convection. Okay, so this is just a picture to compare with normal convection, dry convection or moist convection. Okay, but what's really interesting is that with the mesoscale convective systems, you get this organized convection where you get a downdraft. Well, you have the strong updrafts, a strong downdraft. The downdraft produces wind gusts, strong outflow. You get a gust front boundary here, and the winds from outside are being brought in, like right here, to converge and give you the updrafts. But the gust fronts also initiate more new convection. So air moving up over these gust fronts will trigger some new convection, and the whole thing can get cycled into feedback loops to give you a nice self-organized system of convection. So that's another. This is just some picture because it's easier to take pictures of these things over land than over the ocean. This just gives you a real photograph of a mesoscale convective system, and with some little arrows drawn in to guide the eye of what the motion is like. Okay, now a little bit of math. In 1941, Kolmogorov wrote this paper, a couple of papers, on homogeneous isotropic turbulence. The basic idea is we have to, it's so random, we need a statistical approach. It's composed of eddies, blobs of vorticity with a distribution of sizes. It's non-stationary. The mean, variance, and other quantities vary in time. And what Kolmogorov did, and I don't know if it was ever used before, he introduced velocity increments. So you take the difference between the velocity at some position and subtract it from the velocity at a different position. So in here, this r hat is my r is my observation direction. Okay, so I'm taking the velocity component along my observation direction and looking at the difference between the velocities at two different positions along that observation direction. And the key thing for the probability theorist is the full statistical information is contained in the probability distribution of these velocity increments. So that's ideally what you'd like to have, and you'd like to be able to look at the moments. And the moments are called, in the turbulence literature, called structure functions. And I guess people in turbulence tend to assume that everybody knows that when they say structure function, they mean a turbulence structure function, because other fields also use that term and do not mean turbulence structure functions. So in turbulence, when you're talking about turbulence and you hear the term structure function, immediately think of these moments of this probability distribution. Okay. And that probability distribution is constrained by the physics, and in the case of whatever physics there is, and the physics that Kolmogorov was only thinking about were completely contained in the basic Navier-Stokes equations. Okay, the second order structure function is perhaps one of the easiest ones to get an idea of what it means. So let me spend a little time discussing this, because this is the one that's related to the energy spectrum. So if you consider a sample of length Rn, so just imagine just taking a one-dimensional sample, and now you're just looking at the difference between those 2 points to give you your velocity increment. But there's something else you could also do with that sample. You could calculate the sample variance. All right, so you can just calculate the sample variance. There's a nice standard formula for it that you're all familiar with. But probably what you're not so familiar with is that you can rewrite this term right here, these terms right here, into a sum over velocity increments. It's just that there's lots of velocity increments. You could take this one minus that one. You could take this one minus that one, and so forth. So there's several. So it's just a matter of playing around with the math a little bit, and you can find this relationship. And then you can show, my colleague here, Vogelzong, showed this. So you take the mean of the sample variances, which we call the spatial variance, which depends upon the sample length, and you can show that the spatial variance is related to the second-order structure function of a certain a sample of length m. That one's the longer one of sample of length n, but it's a combination of these other structure functions of different scales, and you can write that in a continuous case. Now, after he derived that and showed it to me, it started to remind me, spatial variance reminded me of some things I'd seen when I was near your age, most graduate students, in the area of fractals. And after asking Mr. Google to help, I found a reference to a paper by Professor Yates in 1948 that had also derived that. That was in context of soil science. This is rather surprising because it never seems to have been mentioned or used in the turbulence literature. But so I hope this sort of outline of how we can relate the second order structure function to the sample variance makes it a little bit clearer. And in principle, we should be able to also, although it's not going to be as simple, relate the other moments of the probability distribution of velocity increments to the other moments of the sample variance. Okay. However, the theory as developed works with the velocity increments. So it's simpler for the Kolmogorov theory to work with those. So that's what we like to concentrate on. Okay, another thing which oh yeah, sorry. If you, one other thing that just to mention in passing is that if you have a power law, say the structure function depends on the separation variable r to some power p, then you can show also that the spatial variance also follows the power law, and if you look at the ratio behaves like that, and so forth. So we've checked these things out with the quick scat data and the scat data, and it's in very good agreement. Okay, some additional predictions of the theory, of the Kolmogorov theory. Okay, basically there's two quantities, the scale r, or separation r, and the mean energy dissipation rate. In 2D and 3D turbulence, the prediction comes out that the second order structure function is Kolmogorov constant times the dissipation rate to the 2/3 power times r to the 2/3 power. Now this is known as the 2/3 law, or if you did it in terms of energy spectra, it would be a k to the minus 5/3. In three-dimensional turbulence, so this is the second order moment, or the width, basically the variance of the, or width of the PDF. The third order moment gives you a nice simple law called the 4/5 law. And this is was derived as an exact result from turbulence theory by Kolmogorov, one of the few exact results in turbulence theory. And this F here is is just equal to minus epsilon, and it's F is because epsilon is positive in three-dimensional turbulence. It's always downscale. Therefore, F is negative. And in two-dimensional turbulence, Eric Lindborg in 1999 published a paper deriving the similar result for two-dimensional turbulence, and you get this expression but F is now greater than 0, indicating that energy is flowing upscale, going from small scales to large scales, small vortices making big vortices. So the question now becomes, what's the best way to work with this? Okay, well, I'm going to go back and I'm going to continue with the concentrating on the PDFs now. So the probability distributions vary with scale R. The second order structure function just gives you the width. The third moment gives you information about its symmetry. And the standard thing in all classical statistics books talks about the skewness, which is just a normalized third order moment. And the question, so if you have a negatively skewed or positively skewed probability distribution. So the key thing that we can test not only is the scaling of the second order structure function, but just the shape of the PDF. Is the PDF negatively skewed? That would be evidence for three-dimensional turbulence. And if it's positively skewed, it would be evidence for two-dimensional turbulence. What happened? Too many buttons. Okay. And here's some theoretical, I got this from a theory paper that did not go, that I've forgotten exactly where they got these probability distributions, but anyway, this is what it is expected to look like in three-dimensional turbulence. It's just skewed just a little bit. The skewness is expected to be minus 0.3, and the two-dimensional turbulence, which is this sort of more faint line, is almost symmetric. It's only slightly positively skewed. So that's the sort of differences that we're looking for. Going the wrong way. And this is the difference between Macintosh and Windows, because it doesn't show by delta. There should be the increment delta UL. Okay, some interpretation of what these increments are is that if we have convergence or some deceleration, spatial deceleration of the wind vectors in space, then delta UL will be negative, and if it's divergence, then it should be positive. And we also have a similar interpretation for the another component to the velocity, but I'll not spend any time on that in this lecture. Just to remind you of the region and these areas. And this is what the PDFs look like for the ITCZ regions, the equatorial regions, and then regions just to the south. And what I've plotted here also, I've got several lines. So there's the blue solid and dashed is for the A scat. The red and red dashed are for quick scat. And the green is a quick scat, but it's been processed by algorithms by the A scat people. Okay, so they have a different approach to to dealing with quality control and ambiguity selection. So basically what this thing is, the blue always lies outside the red, which says that ASCAT is seeing more convection than QuickSCAT because it can see through the rain. But otherwise, the nice thing about it is that they're all pretty similar. But they're different but similar. There's some notable differences down here because this dashed line, this QuickSCAT data for the dashed line is actually produced by NOAA during just a one-year special near real-time data set, whereas QuickSCAT is science quality. So they go back over and reanalyze it and throw at it the best algorithms they have. But the red dashed line was for near real time, so quick and dirty. And it shows you, what that shows you is that there's some like here, shows that there's some artifacts in the near real-time data, which are well known. Okay, so this is the sort of standard notation in the turbulence literature. So the second-order structure function taken along track where the observation direction is along track. And the question is does it behave as r to the 2/3? And what I'm showing you here is that, well, one thing's for sure is that ASCAT and QuickSCAT don't give you the same slope. So over a certain range, the QuickSCAT, which is in red, gives you a steeper slope than the ASCAT. And there's this feature down here where the ASCAT gets very sharp, steep. I mentioned earlier about some onboard processing that we have no control over on this data set. So we have to ignore that part. So the processing matters and the instrument matters. So one next step is we can say, well, how do these slopes vary over time? And so here I select the scales between 50 kilometers and 300 kilometers. That's in the equatorial region, that's basically the range of scales of the weather systems. And you can also just, again, of extra interest here is that this other structure function was taking a look at the differences between the wind components that are transverse to the direction. Gives you a bit of information about the vorticity. Has a different shape altogether from the other two, from the other one. Okay. So if I look at the West Pacific and compare it with the East Pacific, the slopes are not 2/3. So the 2/3 line is this solid horizontal line here and here. And so I'm just showing you here the two QuickSCAT products and the two ASCAT products. The solid lines are the ASCAT 12.5 and the QuickSCAT 12.5 kilometer grid. So you can see the effects of processing. You can see that there's a seasonality, which they all seem to agree on, but that there's a big difference of widespread in slopes. So that's disappointing for the turbulence theorists who are always looking for scaling, but it's very useful for comparing scatterometer products. And it also tells you that the turbulence is very inhomogeneous. It varies in time, varies in space, varies in region. Now let's look at the shape of the PDF. Remember, the skewness has given us the shape of the PDF. And first of all, I'd like to know, is it constant? Well, it's fairly constant sometimes. So here, some variation between product and between an instrument, but otherwise pretty much a green sign. There are some outliers. You see this kind of be very sharp gradients here, here. So those cases bothered me a lot for a long time, but I had found a solution to it. It's a very interesting reason for it, and I'll talk about that very shortly. Down here you see something, more outliers. Remember this dashed red curve is from the near real-time product from the QuickScat, and that have well-known artifacts in it. And again, it shows it's very, very obvious that it's out of character with the other ones. So altogether, for three-dimensional turbulence, we're expecting minus 0.3, and for 2D turbulence, we're expecting something close to 0. And you can see that there are some cases, well, nothing's ever really exactly minus 0.3, but there's things that are not too far from that, somewhere close to that neighborhood, and they're negative, but there's also some cases where it becomes positive. So to take a look at everything over time, what I did is just take the average value of the skewness between that 50 and 300 kilometers, take the average, and see how that varies. So this is the average skewness over that region versus the month of our study period. And you can see in the West Pacific, it's going from something close to what we would say is supports evidence of three-dimensional turbulence to something that looks like two-dimensional turbulence. And you can see in a number of cases where it changed sign. And this is over here, for example, in the East Pacific equatorial region. There's a lot of convection going on, moving into the area during these months. Otherwise, it was back to normal cold tongue type of atmosphere. Over here, you say, well, what could be happening here? Well, it could be these mesoscale convective systems coming in with downdrafts, bringing a lot of extra divergence into the area. So the result here, so circle in blue are basically evidence for something close to two-dimensional turbulence, and everything else something close to three-dimensional turbulence. So that says so that gives us an answer to the original question. Is it upscale energy transfer? Yes. Is it downscale? Yes.